All right, good morning or afternoon, I guess, based on what time you're watching this. This is section 6.5, logarithmic properties. So some general properties of logarithms that follow from kind of their exponential definition. And these should make sense. So let's take a look at them. So log base b of 1 is always 0. And that makes sense because b to the 0 is always 1 for any number b. And this makes sense also. Log base b of b always equals 1 because any number to the first power is just itself. So those things make sense. The inverse property is something we actually explored in the board work the other day. This idea of where if the bases are equivalent, they, for all intents and purposes, they quote unquote cancel out. And so you should remember those from the other day. The one-to-one property, we're not going to use this one much today, but it will be important for the stuff in the next section. The log base b of m is equal to log base b of n if m equals n. And we'll use that when solving equations next. So we'll come back to that one. We are going to use the product rule for logarithms today that follows directly from the laws of exponents where, if you're multiplying exponents, you add them to do that. So it makes sense that to multiply two things inside the argument of the logarithm, that you would then add the logs of those, since we are really working with exponents when we're working with logarithms. So example number 1, we want to expand, which means write it as multiple logarithms, log base 3 of this expression. And so notice it is a product. And what that means is, it's this multiplied by this. And so we can apply those rules for logarithms and write the log base 3 of 30x plus the log base 3 of 3x plus 4. And then you'll see that there is another product that's still inside of here. So we could actually separate this a little bit further and write log base 3 of 30 plus log base 3 of x, and then just bringing down the third logarithm because this is a sum, so we can't do anything with that. So that's all done. So if you want to try one, there's the answer. See if you can get that or see how we ended up there. The quotient rule for logarithms follows similarly from the exponent rules. If we're dividing exponents, we just subtract one for the other, so it makes sense that we would subtract the logarithms as well. So something important to remember here is if you're applying the quotient rule, you do want to factor and fully simplify before doing that. And so let's expand this expression. And the first thing I'm going to do is apply that quotient rule. And I want to say, whoops, that'll be, wow, please stop doing that. Log base 2 of the numerator, 15x, x minus 1, minus the log base 2 of the denominator, which would be 3x plus 4 and 2 minus x. Let's, put some brackets around that so we know that that's one thing inside the logarithm. But now you can see that there's some product rule happening here that we'll need to continue with. So I'm going to start over here because it's going to take some room. This would be the log base 2 of 15 plus the log base 2 of x plus the log base 2 of x minus 1 minus, we need to keep anything we subtract together because we're about to apply this product rule. So this would be the log base 2 of 3x plus 4 plus the log base 2 of 2 minus x. And, just as any time we subtract a sum, we need to make sure that we apply the negative to both parts of it. And so this will be, again, log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1 minus log base 2 of 3x plus 4 minus log base 2 of 2 minus x. And now it's fully expanded, so we're all finished. If you want to try one of these, in number 2, see if you can expand this logarithm to obtain this result. Moving on to the power rule for logarithms. So if we have the logarithm base b of something m to a power n, we can actually swing this exponent out front to multiply by the entire log, and that's super useful. So let's expand this logarithm. So we're going to swing that exponent out into the front, and so that'll be the log base 2 of x times 5. If you want to pause and try number 3, see if you can see how we got this result. And then moving on to example 4, one other thing is we can rewrite the argument of an expression as a power prior to applying the power rule. And so if we're going to expand log base 3 of 25, we can do that by rewriting that as the log base 3 of 5 squared, and then we will have 2 times log base 3 of 5. So if you want to give that one a shot in number 4, pause the video. Recall that a exponent in the denominator can be moved to the numerator by making that exponent negative, and then maybe you can see how we ended up with that negative 2 natural log x. Okay, example number 5, rewrite this using the power rule into a single logarithm of the leading coefficient of 1. That means this can't be a 4, it's got to be a 1. And we can use that in reverse, so this would actually just become the natural log of x to the 4th power. And see, now we have the leading coefficient of 1 like they asked. So if you want to try number 5 and see if you can get this result, pause the video. Right, now let's talk about expanding logarithmic expressions that are a little more complicated because a lot of times we'll use all of the power, quotient, and product rules in a single fell swoop. So let's rewrite then this natural logarithm. And in general, I'm going to handle the quotients first just because that keeps things nice and simple. So we'll write this using the quotient rule, and then we'll rewrite this first part using the product rules. So this will be the ln of x to the 4th plus the ln of y minus the ln of 7. And notice there's one additional rule that can be applied here, and that's the power rule. So we'll swing that out front. 4 ln of x plus ln of y minus ln of 7, and we're all done. So if you want to pause the video and try number 6, see if you can obtain that result. Then moving on to example 7. So let's do this with radical expressions, and this is pretty simple as long as we recall that a square root or a root can be written as a fractional exponent. In this case, it would be 1/2. And then we could just use the power rule to swing that out front as a product, and we're all done. So if you want to try to do number 7, remember that this is 1/3, and then this to the power 2, and you just use the multiplication property of raising exponents to another exponent, and you should be able to obtain that 2/3 fairly simply. For number 8, now this one is or has a lot going on. And so again, I'm just going to go ahead and begin by dealing with that division by writing the the difference of the logarithms, the numerator first, and then subtracting the denominator. Then we can see there's a lot going on still in this argument. And so we're going to need to apply some more rules. And let's do the product rule first. So this will be log base 6 of 64 plus. Now I see that I'm doing something to a power here, so I'll go ahead and apply the power rule also. The log base 6 of x, and then plus the log base 6 of 4x plus 1, minus the log base 6 of 2x minus 1. So in general, I always do the quotients first and then apply the power and product. You can do those simultaneously, or if it's complicated, just do the powers first and then apply the product rule. Or you could do either one, whichever makes sense. I couldn't apply, as a side note, I couldn't apply the power rule to this whole thing because it's not the entire quantity to this power. So that's why I chose to break it apart first, because the only way that would work is if you wrote this as a power of, let's say, power of 3 first. But you don't have to, and that's taking it a little far. unless that's just the way your brain sees it. That's why we practice, so that you can kind of get a handle on what works for you by checking against what you're getting in your process and making sure those are aligned. In number 8, if you want to give this one a try, this is the result you should obtain. So I encourage you, especially with this, to pause the video and try it and see if you can kind of come up with the same thing I did. Now, condensing logarithmic expressions is when we move in the other direction. So we want to write as a single logarithm, and you'll see in the next section why we want to do that. And so we want to condense these using those same rules. And so first thing I'm going to do, just like before, is I'm going to handle the quotients. So I'm looking at the subtraction first. And so this will be the log base 3 of 8 over 2, which is just 4. And so then we'll say, the log base 3 of 5 times 8 divided by 2 is 4. And so this would be the log base 3 of 20. All done. Single logarithm. That's how you know when to stop. So if you want to try number 9, I wrote a note here to remember to reduce your fractions, because if you don't, it won't seem like you got the same answer as me. So make sure to reduce your fractions in your final answers. And moving on to example 10, this one is just getting a little more complicated. So we'll go ahead and apply that power rule first, and then let's do the power rules first. And this would be log base 2 of x minus 1 to the 1/2 minus the log base 2 of x plus 3 squared, all to the 3rd power. So there's some cleaning up I want to do before I even take the next step, because that's looking kind of gross. Before I even continue with the condensing, I'm gonna handle a couple of things here, and I'm gonna write that as a root. And then this, I'm going to go ahead and write this as x plus 3 to the 6, because 2 times 3 is 6. Now I'm ready to handle that quotient rule. So this will be the log base 2 of, the numerator comes first, and then the denominator. And then we'll handle the product rule. So this will be the log base 2 of x squared times the square root of x minus 1 over x plus 3 to the 6th. And there we go. So again, I did the powers, simplify some stuff because that looks gnarly. Then I did the quotient, and then I did the product, and then I knew I was finished because I do have a single logarithm. So if you want to try number 10, I really encourage you to do this, because this one's kind of complicated. And just give you a minute to do that. All right, so example number 11, again, rewriting as a single logarithm. This one's just kind of complex. And so let's handle these powers first, just like we did before. This will be the log of x squared minus the log of x plus 5 to the 4th plus the log of 3x plus 5 to the 1 over x power. That looks crazy, but it doesn't matter, because we just follow the rules. This is multiplied out front, so it can, just like everything else, just be applied as an exponent here. And so now let's do the quotient rule. So this would be log of x squared divided by x plus 5 to the 4th plus the log of 3x plus 5 to the 1 over x power. And then we can apply the quotient rule. And remember, when we are multiplying expressions together, especially a rational expression like this, everything is assumed to be in the numerator unless it's clearly shown to be in the denominator. And so this is a single expression written as a single logarithm, so we know we're all done. Even though it looks quite complex, we just follow the rules. If you want to try number 11, pause the video and see if you can obtain the same thing I do. All right, so this is an application problem. And so let's talk about what all this stuff means. So in chemistry, pH is a measure of acidity. And that measurement is based on the number of active positive hydrogen ions in a solution. And so in H plus is the concentration of hydrogen ions, or positive hydrogen ions. And so that relationship can be described with this. And so it's using logarithms. And so let's say if the concentration of hydrogen ions in a liquid is doubled, what is the effect on the pH? So let's say that, let's call P be the original solution's pH, and let's let C be the original H positive concentration. All right, so we have the following relation. We have P equals negative log C. Okay? And so now to obtain our new equation and relationship here, the new pH, and this is the new solution, pH is given by negative log of 2C, because we've doubled the concentration. And so using the properties of logarithms, we can rewrite this using the product rule as the log of 2 plus the log of C. Rewriting again, we have negative log 2 minus log C. But if you look up here, we can make a substitution because P is equal to negative log C, and we have a negative log C here. So I'm going to remove that negative log C and replace it with P. And you'll see why that's happening in a second. So this would be plus P. And so the new pH can be described by taking the original and subtracting log 2. And so what we'll find is that, let me go grab my calculator because I lost it. Give me 2 seconds. So that'd be approximately 0.301. So we would have pH equals P minus approximately 0.301. And so what we can say here is the original question said, what is the effect on the pH? Well, the effect on the pH is that the pH decreased, because it's subtracting, by about 0.301. And so that is how we can determine the effect on doubling the concentration of those positive hydrogen ions in the pH of the solution. So even though we doubled the concentration, our pH only decreased about 0.301. And so you'll use that same process each and every time. So if you want to try one of those, go ahead and do that. And then finally, using the change of base formula. So change of base formula is great. So you can take any base and change it into, notice these are written in the bases that we can use in our calculator, the natural logarithm and the common log, or the base 10 log. And so that's really useful. So this, in example 13, I can't put that in my calculator. However, I can put the log base 10 of 3 divided by the log base 10 of 5 into my calculator. And we can also do this with the natural logarithm, which enables us to kind of answer the question. So this is the quotient of natural logarithms. And then finally, evaluate the log base 2 of 10 using the change of base formula with a calculator. And so what you would need to put in, you can use the natural log, or you can use the common log. I'm just going to use the common log. That's just kind of the habit I'm in. You can do whatever. So the log base 10 of 10 divided by the log base 10 of 2. So the log base 10 of 10 is 1. And then the log base 10 of 2 is about 0.301. And then you just place that in your calculator and you'll obtain the final result. And so that'd be 1 divided by, that would be about 3.322. And so now if you want to give it a try, in number 14, that'll be our last example of the day.